Right now, there are more than 10,000 active satellites orbiting Earth. GPS, weather forecasting, internet, military communication. Almost everything modern life depends on runs through something we can't even see, spinning silently overhead. And here's a question that sounds simple, but genuinely isn't. Why don't they just fall down? Gravity hasn't gone anywhere. Earth is still pulling on every single one of them, all the time, with exactly the same force it pulls on everything else. So what's actually keeping thousands of multi-ton machines suspended hundreds of miles above our heads? The answer isn't some anti-gravity trick. It's something stranger. And once you understand it, you'll never look at the night sky the same way. So today, we're breaking down exactly why satellites stay up, how they got there in the first place, and what it would actually take to bring one down. Let's get into it. Here's the twist that answers our opening question. Satellites aren't defying gravity. They're constantly falling. The reason they never hit the ground comes down to speed, not some force pushing them up. To stay in orbit, a satellite has to be moving fast enough that as gravity pulls it back toward Earth, the curve of its fall matches the curve of the Earth itself. In other words, it's constantly falling, but it's moving forward so fast that it keeps missing the ground. For a low Earth orbit, roughly 200 to 1,200 miles up, that means traveling at around asterisk 17,000 miles per hour. That's fast enough to circle the entire planet in about 90 minutes. This is why rockets don't just fly straight up. After the first phase of launch, they begin a maneuver called a gravity turn, gradually tilting sideways, trading vertical speed for horizontal speed, because horizontal speed is what actually keeps something in orbit. So now we know why satellites stay up once they're moving fast enough. But how do they get that fast in the first place? That's where the rocket comes in. Every orbital rocket launch starts by fighting one thing above all else: Earth's gravity and the thick atmosphere sitting right on top of the launch pad. Most modern rockets are built in stages, separate sections, each with its own engines and fuel, that are jettisoned once they've done their job. This matters because carrying empty fuel tanks is dead weight. Dropping them mid-flight makes the rest of the rocket dramatically lighter and more efficient. The first stage is the biggest and most powerful section, designed purely to punch through the dense lower atmosphere and get the rocket moving fast. This is where the most fuel is burned, and where you see that massive, thunderous liftoff everyone recognizes. Companies like SpaceX have changed this part of the process significantly with reusable first stages, boosters that separate, flip around, and fly themselves back down to land on solid ground or a floating ocean platform, ready to be refueled and flown again. Before this became routine, first stages were simply discarded into the ocean after a single use. Once the first stage has done its job, it separates, and a smaller second stage takes over. By this point, the rocket is already moving incredibly fast and is well above most of the atmosphere, so its engines can be optimized differently. Designed for the vacuum of space, rather than for pushing through thick air. This is where the gravity turn continues, gradually shifting the rocket's trajectory from mostly vertical to mostly horizontal. The goal is to reach a specific target, the right altitude, combined with the right horizontal velocity at exactly the right moment. Get the timing or angle wrong, and the satellite won't reach a stable orbit. It'll either fall back to Earth or head off on an unintended trajectory entirely. This is why launch windows are calculated with extreme precision, often down to the second. Once the second stage reaches the target orbit, it's time for the moment everything has been building toward: satellite deployment. Depending on the mission, this can look very different. Sometimes it's a single large satellite, released using springs or small pneumatic pushers to gently separate it from the rocket without damaging sensitive equipment. Other times, especially with companies deploying large satellite constellations, it's dozens or even hundreds of smaller satellites released in a sequence, like seeds being scattered along the rocket's path. Once released, the satellite is now on its own, already moving at orbital velocity, technically already in space. But its job is far from finished. Solar panels typically unfold to begin generating power. Antennas and instruments deploy. Onboard computers run diagnostic checks. In many cases, small onboard thrusters fine-tune the satellite's exact position, nudging it into its final, precise orbital slot. If everything goes according to plan, the satellite is now stable, powered, and functional, ready to begin doing whatever it was built to do, whether that's beaming internet to remote areas, tracking weather systems, or relaying GPS signals to your phone. Here's something that surprises a lot of people. Not every satellite goes to the same kind of orbit. Where a satellite ends up depends entirely on what it's designed to do. Low Earth orbit, roughly 200 to 1,200 miles up, is where you'll find the International Space Station, most Earth observation satellites, and large internet constellations like Starlink. It's relatively cheap to reach and offers fast communication with minimal delay. But satellites here move quickly across the sky and often require large networks working together to provide continuous coverage. Geostationary orbit, roughly 22,000 miles up, is reserved for satellites that need to stay fixed above one exact point on Earth. At that specific altitude, a satellite's orbital speed matches Earth's rotation exactly, so from the ground, it appears to hang motionless in the sky. This is where most weather and television broadcast satellites live. There's also medium Earth orbit sitting between those two, which is where most GPS satellites operate, a balance between coverage area and signal delay. Choosing the right orbit is just as important as the launch itself, because it directly determines how the satellite will actually be used once it gets there. So if satellites are just endlessly falling and missing the ground, does that mean they stay up forever? Not quite. In low Earth orbit, there's still a faint trace of atmosphere. Not enough to breathe, but enough to create tiny amounts of drag over time. That drag slowly saps a satellite's speed, and once it loses enough velocity, it can no longer outrun the curve of the Earth. It begins spiraling lower, faster and faster, until it eventually burns up or crashes back down. This is why many low-orbit satellites, including old rocket stages, eventually deorbit on their own after months or years. Higher up in geostationary or medium orbits, atmospheric drag is essentially non-existent, so satellites there can remain in orbit for an extremely long time, which is also part of why space debris in those regions is a growing long-term concern. Beyond natural decay, it's also worth being honest that the launch process itself is genuinely difficult, and failures still happen, even with decades of accumulated experience. Engine failures during ascent, guidance errors that send a rocket off its intended trajectory, stage separation malfunctions, or a satellite failing to deploy correctly after reaching orbit. Any one of these can end a mission that took years and enormous amounts of money to prepare. This is part of why reusable rocket technology has been such a significant shift in the industry. Beyond cutting costs, reusability allows companies to launch far more frequently, which means more real-world data, faster iteration, and, over time, improved reliability across the board. Even with a strong track record, though, space remains an unforgiving environment. There's very little room for error once a rocket leaves the launch pad. So the next time you check the weather, use GPS to find your way somewhere, or stream something over satellite internet. Remember what actually made that possible. A precisely engineered explosion, a carefully calculated gravity turn, and a piece of hardware released at 17,000 miles per hour, trusted to fall around the Earth forever instead of falling back down to it. It's one of the most quietly impressive achievements of modern engineering, and it's happening above your head right now. If you want to keep exploring how modern space technology actually works, hit subscribe to Deep Space Files, because the science behind the sky is just as fascinating as what's beyond it.